Welcome to the kinematics of rigid body motion. Today we are going to discuss orthogonal transformations. To begin with, we are going to relabel the set of coordinates x, y, z by x1, x2, and x3. And we are going to relabel the director cosines ij simply as the quantities a of labels I and j. Just for convenience of notation to make things to make derivations easier to carry out. Now, previously we have obtained the sets of equations 4.5 and 4.6, which give the linear or vector transformation from the laboratory coordinates to the primed coordinates, and they are given in the form here. So they are the primed coordinates. Each of them are given as a linear combination of the laboratory coordinates, having the a's as coefficients. The above, so the ones here, are less general than the transformations of equation 138. We defined back in the survey of elementary principles. So those were transformations relating Cartesian and generalized coordinates. So these are a special case where we simply go from one set of Cartesian coordinates to another through a linear transformation. We can simplify the notation even further using Einstein's summation convention, which we have employed previously, but I will also remind it here. So we can write any primed coordinate as the linear combination here for all values of the index I, and something like for example, the sum of the squared components of a vector can be written simply as here. So we always sum of over the double indices. So we see that equations for given by 411 are a special case of the set 4.12, as not all direction cosines are independent, since they are being constrained by the relations 4.8 we have derived previously. However, one thing to keep in mind is that the vector length is invariant to the system used. So both in the laboratory and in the primed coordinate systems, the length of a vector must be the same. So the sum on the sum of squares on the left hand side, which is the length of the vector in the primed set, must be equal with the length of the vector in the laboratory frame, which is given by the sum of squares on the right hand side. But then the left hand side can be expressed using the relations here to expand into the following form, and we can see that this will reduce to the result here if these two sets of conditions are met. So when j is equal to k, the summing over the index I in a product of these coefficients must lead us to 1. And if j is different from k, then the sum of the products of the coefficients is equal to 0. And we can put these two conditions together once again by using the Kronecker delta symbol to obtain the condition here, which is so the sum over the index I, and it must hold for any combination of coefficients j and k going from 1 to 3. This is known as the orthogonality condition. It is equivalent with equation 4.9 if 4.11 holds. And any transformation of the type 4.12, for which 4.15 holds, is called an orthogonal transformation. Such a transformation takes place when going between two Cartesian coordinate systems having a common origin. The transformation matrix is given uh, by the expression here, where the coefficients a of index I and j become the matrix elements of the transformation. As an example, if we rotate in a plane, the matrix simply becomes the form given here. Because so what we're saying is, clearly what we are saying is that we are rotating about an axis that is normal to the plane. And so the orthogonality conditions here will lead to free constraint equations, which are straightforward to see by applying the general condition. So there is a single degree of freedom, namely the angle of rotation phi, which follows from the fact that the axis of rotation is fixed, being normal to the plane. Therefore, if we write the primed coordinates, so the rotated ones in terms of the fixed coordinates, we can identify uh, the elements of the transformation matrix and write it accordingly as the familiar expression here. Now, the matrix A can be thought of as an operator changing the unprimed frame to the primed one, which is expressed by the formula here. Or said in other words, the matrix A acting on the components of the vector in the unprimed frame produces the components in the primed frame. In this interpretation, the matrix A acts on the coordinate system, leaving the vector itself unchanged. We merely ask for the components of the same vector in two different coordinate systems. However, one can think of the transformation where the vector is changed, with both initial and final vectors being expressed in the same coordinate system, which would be written as here. These two pictures are fully equivalent, with the formula 418 representing a trigonometric rotation of the frame, while formula 419 is an anti-trigonometric rotation of the vector. When the operator acts on the coordinate system, we speak of a passive transformation, which is the kind of transformation that is useful in rigid body dynamics. If the operator acts on the vector, we speak of an active transformation, which has more widespread application in other fields of physics. In summary, we have derived the orthogonality condition and found the orthogonal transformations that preserve the length of vectors. We have shown that an orthogonal transformation can be represented as a transformation matrix and that such a matrix can correspond to the rotation of a vector in a plane. We have discussed the meaning and equivalence of passive and active transformations, and in the following we will discuss formal properties of the transformation matrix. So, all that being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.